Everyone, I think we can start at last. Lydia, just wave or something if there's some problems with the stream. We're doing this a bit domestically today, or artisanal. It's very delayed. It's like 30 seconds delay. Don't worry about this. On Zoom, you can see real time. Okay. All right. So welcome to this course. And what is this course? I called it Quantum Physics for Non-Physicists. You should be able to hear me, right? What it says on the tin. So the idea of this course is to kind of give you a solid introduction to quantum physics. So good enough that you'll be able to. This is the other Lydia. Any newspaper and she'll be monitoring science article about quantum scientists do X and understand if like this is serious science and what is actually meant by this. So we'll cover in terms of material, we'll cover everything from what is a qubit, how measurements work in the lab, and all these kind of buzzwords that you hear a lot like spin or uncertainty principle, interference, quantum superposition, entanglement, entropy, these kind of things. We will cover this, and by the end of the semester, you'll know what they mean, and it's really no mystery. In terms of technical things, the farthest we'll get is to derive the behavior of an hydrogen atom, which is kind of in a way, it's one of the few systems that are both physically relevant and you can solve analytically. So the idea of quantum mechanics is that you have very simple rules. From these simple rules, you can derive a lot of complexity. But if you actually want to calculate anything, at some point, you just need to do numerical calculations. But we'll see what is this, okay? And in terms of interaction and overlap with other courses, so there's Quantum Mechanics 1. This covers maybe more or less the same material, but they have more of a historical approach, and ours is more information theoretical. So I think it will be, I'll try to make it much more friendly for non-physicists, which you are. Then there's a course of quantum information theory, which this semester is given by Philip Carmelander. He's an excellent researcher. And in the next semester, there's quantum information processing, which is kind of introduction to quantum computing. So the difference is that this course is about the physics, and the other courses are more about how we manipulate quantum information or how we do quantum algorithms. They are complementary. If you take this one, then the other two will be very easy. Philip let me know that the other course, QIT, Quantum Information Theory, you can also watch everything online. Good. In terms of what background you need for this course, well, you need a little bit of linear algebra, but this is really just at the level of multiplying matrices, computing eigenvalues, and we'll do recaps in the tutorials, and there's the appendices of the lecture notes. So if you don't remember anything, don't worry, just ask, and we'll go through it. And we'll need a little bit of calculus, like you have to have seen integrals before, but again, we'll do them very slow and we'll not do anything too difficult, I don't think. Okay, and a bit of probability theory, which is very, very basic. So you can tell that I'm a physicist because I will talk a lot with analogies and metaphors, which is what we do because maybe because we don't share a language with other scientific communities, I don't know. So to give you maybe a difference between the way this course is given and other quantum physics courses are given, it's best to have like a football analogy. Because in physics, it's like we're out there watching a game happen and we're trying to figure out the rules, but we cannot just ask someone for the rules, right? We go to the lab and they make experiments as observations and they try to figure out what rules it is like. So imagine at the beginning of the 20th century, it was like scientists had been watching a football game for a while and try to work out what the rules are. And you go like, okay, well, I think they can only touch the ball with their feet. There's two teams, they have 11 players. There's one special player that can touch the ball with their hands. And they try to put the ball in the other people's goal. And then they score points and there seems to be a time limit. And maybe we can work out the details later about what's the yellow card, what's the red card, but these are the basics, right? And this was kind of the setting, but with classical physics, right? They thought, okay, we understand how light works a little bit. We can shoot it through a prisma and makes a refraction, and we can study these things. We understand classical dynamics very well. There might be some details to work out, but that's it. But then, like in the football game, maybe you start asking yourself, well, wait a moment. Then why doesn't the team always leave an attacker very close to the goal of the other person, like all the time there of the other team, right? It would make sense because then they could just, whenever they get the ball, they shoot it to the other side, and then it's like very likely to get a goal. And then I think, but there must be some rule that does not allow for this, because if it was, it would be a very different game, right? Then the defending team would always also leave some player behind, and this is not what we watch in a football game. Like they all come to the one side of the field or to the other. So what's going on? And then you discover the offside rule, right? And this is the rule that, well, you cannot actually leave someone there, or they can stay there, but they cannot receive the ball there. And this kind of completely changes the game. It changes the nature of the game, even if it is something that you did not realize after watching 10 football games, right? And with quantum physics, it was the same thing. So they thought they could explain everything, but then at some point they start observing, I don't know, the light spectrum of some elements, what happens when you shoot some kind of light into a copper solution or so, or the black body radiation. And it just did not behave in the ways that the rules that they had could explain. So then they come up with, after a lot of agonizing, they came up with the rules of quantum mechanics. And then from a very simple set of rules, we can derive everything else. We can now make sense of this game in most regimes at the small scales. Okay, so that's kind of the analogy for the historical introduction. If you take a quantum mechanics 1 course, then the first third of the semester is in this process of like, they're trying to figure out this rule. Then they did this experiment, then they did that experiment, and so on. This is equivalent to me to if now I did all this observation of football and now I want to explain the rules to you. I don't necessarily want to tell you this whole story and all the things I did and all the faults I failed and so on. I might just want to give you the rules and then you can play. So that's what we'll do here. So in particular, in the first lecture or two, you need to be a bit patient, because it's like when you arrive to a board game session and the first hour is spent just explaining the rules. So that's what we'll be doing today. Okay, so I'll give you a lot of formalism and then we can start playing with it. Okay, so after this long introduction, maybe we'll start with the first part. So we'll talk about quantum states, how to represent them, and then we'll talk about a little bit about measurements, and then next time we'll talk about the evolution of quantum states. Okay. So so let me call quantum and some examples to keep connected to the physics of what we'll be talking about. This could be things like electrons, photons, atoms, but also more complex things like a whole circuit in a lab, right? For example, a superconducting circuit. But also like people really, like we are all made out of quantum particles, and there's no like obvious place where the laws of quantum mechanics stop applying, right? So we're all made of like everything around us is quantum. The one exception is that people don't know very well how quantum mechanics yet interacts with relativity, and that's where we start having problems. But at a scale of like human beings that are not moving anywhere close to the speed of light, quantum mechanics is more than enough to explain everything. Of course, it might not be the most efficient way to do it, right? You don't explain like psychology by looking at the behavior of electrons. You have kind of effective models at different scales. But just know that it's a matter of kind of degree, not something fundamentally different. Okay, so how do we represent a system? In the same way that in your computer, you can store information as bit strings, and then it's like minimal unit is a bit that can be in a state 0, 1. You probably already heard about qubits. And more generally, I'll write some more complex words and then I'll explain what this means. So the state space, please ask questions if something is not clear, is what is called a Hilbert space, which for practical purposes, you can think of it as just a space of vectors, and I'll tell you more detail. So this is a complex vector space with an inner product. Okay. So, oh. Okay. Good. So what do I mean by this? So for all practical purposes, most of the time when you talk about finite systems, and I'll get into the difference between this and that in a moment, we mean things like vectors, with some entries where all these entries are complex numbers. Okay, so think of just a column vector. And you can represent the state of particles through objects like this. These all belong to C. Okay. And the Hilbert space, normally we denote by H. And if we have several Hilbert spaces, we'll get to this later. We call it like H of system A or H of system B and so on. But for now, today we only talk about a single system. Okay. So we have here all these complex numbers, but now there's like two cases that matter. So if you think, let's go back to our examples. So if you think of electrons and photons and atoms, and now let's think about what kind of properties they have. So they have a property like the position or the frequency, right? This seems to be a more of a continuous degree of freedom, meaning the position maybe could take, if we measure the position, in principle, it could take any value in the real line. Of course, in practice, it won't be like this, but it can be represented by a continuous system. But they also have properties that are discrete systems. So this is the case of qubits that can be made of many things. But for example, in the electron, it has some property that's called a spin. We'll talk about this a lot. But just know that it will be represented by a Hilbert space of dimension 2, and we'll talk about it in a second. And it's just something that reacts to the magnetic field. If you turn the magnetic field, the electron will go up or down depending on the spin. We'll explore this later. Then they also have some properties like mass and charge and so on, and we don't worry about those for now. But the point that I'm trying to say is that, well, there's systems that are discrete and systems that are continuous, and it's more or less the same, but we need to be able to work with both. So this here is a discrete system of dimension given by the number of entries in each vector. So let me give you the simplest example. Is a qubit, which means it has dimension 2. And it's the quantum generalization of the bit. So this means that a state can be represented by only 2 complex numbers. Okay, and later we'll see that there's some constraints on these numbers, but for now it's just 2 numbers, right? That you write in a vector on the computer. Now, sometimes it's, very often it's much more practical to find some other ways to write this down. So let's write it first as alpha times this vector 0, 1 plus beta times this vector, sorry, alpha 1, 0, beta 0, 1. Okay, I didn't do anything, so alpha is a number. So multiplied by here, you get alpha here, and this is just a number, right? And why did we do this? Because, well, 1, 0, and 0, 1, they form a basis for this space, meaning that, well, they're orthonormal, and we'll get to what this means later. I know you know what it means, but what it means in the notation we'll introduce, and they span the whole space. So this forms a basis because, so this 0, 1, 1, 0 is a basis for my Hilbert space of dimension 2. And we call it normally the Z basis or the computational basis. The Z basis, we'll see why at the end of the lecture. And computational is because it will look very much like bits in classical computing. So far, you with me? Did not introduce too much. And the idea here is that you represent things like, oh, an electron with a spin pointing up by just changing this coefficients alpha and beta. Or later on, the same for more complex systems. So we introduced some notation here because we don't want to write all these vectors all the time. And there's a notation that we'll see very soon that is very compact and convenient. That is called Dirac notation. And introduces something we call ket. And a ket is just a column vector, really. So we call 0 this one, and we call 1 this one. And you represent it like this. So this is a dash, and this is like a plus sign, larger sign. Okay. So we call that basis that we saw there, we call it the 0, 1 basis. If it had a larger dimension, it would go 0, 1, 2, 3, 4, and so on. Okay. And physically, the things this correspond to is, again, like I said, like the spin being pointing in one direction or the other, or the polarization of a photon being against one direction or another again. But we'll see examples later. So for now, don't worry about this. We just know that, well, this is one basis for the Hilbert space. We'll see more later. And how do we express then a state? So we have this. And as we saw before, we can just write it as alpha. It's 0 plus beta 1. Alpha and beta are complex numbers. And normally we give this, if it's a state we care about, sometimes we give it names. And psi is a very favorite name of quantum physicists. And now let me just do something that normally is compression. For such small systems, it does not look like compression. So I just write this as a sum from x going from 0 to 1 of x times the number psi of x. Okay? Where here, of course, psi of 0 is 0 alpha, and psi of 1 is 0 beta. So it looks like I'm just creating a necessary new notation here, but it will be useful in a moment. First, note that you can expand any state into dimensions into this base. Okay, so you can characterize the state once you fix a basis. You can characterize the state just by these numbers here, and these numbers here are what we call the wave function. And you'll see it's more obvious why we call it that in the continuous case, but let's just see this thing here. It's what we call the wave function. That's it, just the coefficients that you put behind some basis element for some expansion. So this was a discrete case. So far, so good. I've not told you yet what these coefficients mean, what do they mean in terms of like, okay, now how does the system behave depending on these coefficients, or what happens when I make a measurement? We'll get to this later. But first we want to see the continuous case. So continuous, let's say, for example, 1D system. And this can be, for example, imagine you have some particle on a line and you want to know its position, and the position forms a basis for the space. So it's a space that is so large, it becomes continuous. It's an open debate whether a continuous spaces really exist in reality or just an approximation. But so, for example, suppose you have the basis formed by all states x, and now x can be any real number. And I tell you now that this is an orthonormal basis, and we just take it for granted. So then again, we expand a state, any state, just like we did here. What happens to sums when we go to continuous systems? They become integrals. That's it, right? It's just a, think of it as just a glorified sum, really. So we need a dx, x, and now just like before, here come the coefficients. And this is these coefficients are called again the wave function. And in many cases, we'll see that once the basis is obvious, we just work directly with this thing here. And because now it depends on this psi of x depends on x, and x is a real number, then we can think of it as really like a function. We'll see that for many cases, we actually work with the function directly. Okay. So we introduced kets. We saw how to expand them. But actually, most of quantum mechanics will depend on this inner product. In order to have the inner product, we need to introduce Bloch. So this is the and for now, it's just a mathematical trick. So we had this kind of symbol, and now we make this kind of symbol. This is what is called a bra. The reason is that later we'll put a bra and the ket together and makes a bracket. And what is this? Well, this is taking the ket and taking the complex conjugate, meaning that columns become rows, and every complex number in it becomes the conjugate. So the space of these people, depending on the notation, you call it different things, but it's like a copy of the Hilbert space, where everything is just rows instead of columns. You can be more or less rigorous in what these things really are, but for now, don't worry about it. So for example, yeah, our side that was this alpha beta, which was alpha 0 plus beta 1 with qubits. Now the bra is going to be a row where this is the complex conjugate, right? Sorry. Yes. Yeah. I meant here transpose conjugate, right? Yeah, there I know. Right. And this you can write again as being the complex conjugate of alpha. And just so, if alpha is some number a plus bi, then alpha star is a minus bi. Right? So this is alpha 0 plus beta star 1. Okay. they will become useful very soon. And what is 0 and 1? Because they are the brush. So again, we take 0. Where is 0? 0 is this. Now we flip it and we take the complex conjugate, but the complex conjugate of 1 is just 1 and of 0 is just 0. So this is 1, 0, and this is 0. Okay. All right. What happens in the continuous case? You can think about it while I erase the board. It's going to be the same way. So again, the example in the continuous case, if you had some other state psi that was the integral, so I'll just omit, but it's always from -infinity to +infinity in this case. X. Then when you have the bra, it's just going to be the integral dx here, the bra for the basis element, and here this complex number gets conjugated, right? That's it. So with these elements, now we can talk about the inner product between two things. So how is the inner product defined? It's the bracket. It's defined like this. And this is kind of short notation for what? For just having this thing times. Now, if you think a bit about it, this is a row vector, this is a column vector. So the result, it's going to be just a number. Remember, they have the same dimension. We're talking about the same Hilbert space. So think about it, that this is going to be a row vector like this. There's going to be a column vector like so. So the result of this is going to be this element times that, plus this times that, plus this times that, and so on. So it is a number that belongs in C. Yep. And if we wrote, no, we'll do it through one example and then we go for a break, I think. I know, we still have plenty of time. Okay, so then let's do an example. Suppose that psi was our friend, alpha 0 plus beta 1. Suppose that phi, I need two more Greek letters, delta 1. So then what is psi phi? Well, we take this one and we put it in row form. So that's, let's do it first in without Dirac notation, then we do it with Dirac notation. This times that. Sorry. Gamma delta. And what is this? That's just alpha star, gamma plus beta star delta, which as you see is just a number. Okay. What if you wanted to do the inner product the other way around with the phi first and the psi after? It's good to do it for practice, so you can try to do it on your own now too, but let's see. you wanted to do this. And again, it's just maths, but it will be useful later on. So this would be gamma, delta, alpha, beta. That's alpha star plus beta delta star. But that's just the complex conjugate of this, right? We just swap the stars in all the numbers. That's 5. It's this number, but the complex conjugate. And this is true in general, so that whenever you have this, this is always, I'll write it here. Is always the same as changing the order and taking the complex conjugate. And it's kind of this property that makes this whole thing a Hilbert space, if you care about that. Okay. So far, so good. I've not told you what this is good for yet. But essentially, every time we need to compute anything from what's the probability of getting a measurement outcome that we'll see in a second, this depends only on the inner product. It's also very useful if you want to change basis. So if you have a state in a basis and you want to change it to a different one, we'll see how to do it in a moment. Okay. So now that we have a notion of in a product, we can express what it means to be an orthonormal basis in this notation. So what is an orthonormal basis? And this will be useful in a bit, so forgive me for repeating some maths. So the idea is that first of all, it must span the Hilbert space, right? So I have a basis X where the range of X is in some set. It could be 0 and 1, or it could be all the real numbers. So first it needs to do this, and second, it needs to be orthonormal, meaning that if I take two basis elements and I compute the inner product, this must be a delta function, which in the discrete case is just a normal Kronecker delta, very easy. In the continuous case, a bit trickier, but we'll look into it. So for example, the Z basis that we saw, we have that 0, 0. What is this? This is 1, 0, 1, 0, which is 1 times 1 plus 0 times 0. That's 1. The same goes for 1, 1. And if you do 0, 1, well, you swap here, so it gets 1 times 0 plus 0 times 1. That's 0. So every time you have a set of states, you want to test if there are bases, then you run these two tests, essentially. In the continuous case, we need to be a little bit more careful, because now this delta is a Dirac function, but we will not care much about the details. We just need one property. In the continuous case, so we just need this property of the function, so it's 0 if x is different from x prime, which is the same as the discrete case. And then it's not like when they are the same, this thing is 1, but what matters is that integral evaluates to 1. So if I have some integral of dx delta of x minus x prime, and then some function inside this integral f of x, this whole thing evaluates to just the function at this point. We will see examples in a moment. So for example, you can expand the basis, these basis states, x prime. Well, let's just expand it in its own basis. So we can write it as dx. The integral goes in the usual way. And then just have here delta of x minus stack, right? This, if we apply here, well, this f, you see, it doesn't need to be just a function. It can also be a vector or whatnot. This will just evaluate to x at this point, x prime. This will be useful because now let's look at inner products in the continuous case. And let's first do a very simple example of the inner product in the continuous case. So let's see what happens if I do the inner product of the basis, one basis element with my state. So, and this is kind of important that you see how it works, because I put here the integral. I'm just expanding this state in its basis, right, like we saw before. But now look, this is a glorified sum, so it can go on the outside. This is just a row vector. This is just a complex number, so it doesn't matter. The row vector can kind of commute with it. So in the end, we just have the row vector here. So let me write it of the x, psi of x, and here goes the inf. And now we have x prime, and now x that was there before. But now this is an inner product, which you know is this delta of x minus x prime, which means what? Means that this whole function just evaluates to So this is another way of moving between a vector, state, and the wave function. And you'll see later on this will be very useful. We'll do this many, many times. So if you don't follow now, it doesn't matter. But it's just you do the inner product with the basis element at some position x prime, and you get the wave function at position x prime. Yeah. And for now, you just have to trust me that this will be useful. Another one very useful thing that we'll see right after we'll see now and we'll see after the break on application. It's the inner product between now more complicated case of two arbitrary vectors. So, I should have gotten this by now, no? Okay. So let's just take some vector phi and some vector psi in the continuous case. Okay, let's do it. So we have one integral. Let's write this variable x prime. Now remember, because it's the bra, it's the complex conjugate of the wave function. And because it's a bra, this is the bra that goes here, multiplied by the other state, the x, psi of x. Okay. I just use different integration variables so we can distinguish them. Okay, so we need to multiply these two things. And again, remember that these are just really sums, and these are really just complex numbers. So what we get the two integrals, the x prime, the x, then we have the two complex numbers here. and then this 2. Right. And this, again, we know that this is the delta, which means that we can get rid of one of these integrals. What did I miss? X prime, yes, sorry. That's an X prime there, yeah. Okay, so we can get rid of one of them, and it doesn't really matter which one we choose, but at the end of the day, we just have the integral of the X of now the wave function X and the wave function X. And just like before, just like in the discrete case that it's still there, and then we get this kind of complicated sum, but it's really just, it's just a sum, it's just a complex number at the end. And here's the same, right? It's an integral, but at the end of the day, it's just a complex number that comes out of it. Now, this will all be useful because as we'll see very soon, all the measurements depend on this kind of creatures, this kind of inner products. But I think now, yeah, now is a good time to take a 15-minute break, and we restart at 1/4 past. And if you have questions, you can come to me now. Yes, 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 of course. Maybe, is it muted now? Or, yeah, can you mute this on Zoom? Yeah, thanks. Yeah.
Basically, what I wanted to understand is, why did we again define the integral here for the because I kind of missed this point then.
Sorry?
Basically, when we started talking about orthonormal basis, introduce the integral here. When?
So I'm just explaining what Who was it?
Raphael.
Raphael, do you still see us and hear us well?
Maybe he's taking a break. But we can, yeah, like.
Still on? Still on? Yes, sir? Yes.
And you need focus or no? Okay, yeah.
Thank you. What did you do last time to fix? Here it is. No, it is. How did you fix it last time?
Sometimes you have to turn it off and on and then it works. Actually, it's my microphone.
All right. I'll mute now and then you can. Okay. So let's restart maybe. Can I? Lydia? Yeah, I can restart? Okay, yes, all right. So I'll finish the content for today and then I'll tell you a little bit about the course logistics and the tutorials and the exam and so on. Okay. All right, so we showed here how we can, from the state, recover the wave function. That's again just a number, right? You just do the bracket, you just do the inner product with the basis vector. We'll do the same for the discrete cases, even though for qubits is really very simple, just for practice, because we'll need it later. Then we talk about different bases, and then we'll talk about measurements finally. Okay? And you end the day knowing how to compute the measurement probabilities in a quantum measurement. So again, in continuing in the discrete case, example, I can again recover the wave function by doing this 0 in a x in a product with my state, because now x, for example, we looked at the qubit and x is 0, 1. Let's just put 1 here, one of them here, like the 0. And what's this? So this is 0 times the state, alpha 0, beta 1. And this is again alpha. Alpha is just a number. It's associative. And distributive, sorry. Distributive, so it works like this. And this was a 0 still. And now what we know, we computed before. Here, it's an orthonormal basis, so this is 1. And this is 0. Okay, you can still write it as x of 0 minus 0, delta of 0 minus 0, and this is delta of 0 minus 1. Okay. So at the end of the day, you recovered alpha, which the way we called it before is like the wave function for value 0, right? Okay. So in the discrete case, this delta is very simple. Like whenever there's the same element, it's 1. Whenever they're different on the same basis, it's going to be 0. In the continuous case, you apply this Dirac delta property. So you need to like use it to get rid of one of the integrals, essentially. Okay. So now we have all the ingredients to talk about normalization. So far I just told you that the states, the vectors, have some complex number as entries, but we can restrict it a bit more. And this is purely convention, but it's a convention that makes sense. And you'll see why in a moment. And the condition is that if you're talking about the quantum state of some system, then it's normalized, meaning that the inner product of it with itself is 1. We'll see in a moment that this is such that when you make a measurement, if you want to sum up the probabilities of getting all the outcomes, you should get 1 at the end, right? And the probability of getting 0 plus the probability of getting 1 should be 1. And this comes from this condition, okay? But the physics doesn't really change. It's just a matter of rescaling these complex numbers inside here. So what does this mean in the continuous case? Well, this means that 1 must be this in the product, but we already computed it there. So this is the integral dx of the complex conjugate of the wave function that comes from the first one, and from the second one comes this. And what is a complex number times its complex conjugate? That's just the absolute value, right? If you have A star times A, that's just the absolute value of it squared. So that's okay. And this just means the modulo square, and that means precisely that. Okay. So that's in the continuous case. So we have this condition that the wave function must be normalized, and that means that that the integral of the square of the modulus is 1. In the discrete case, well, we have again that what is inner product in the discrete case we saw for qubits, but in general it's always the same. It's X is now the basis element, and it's right. So in the qubit case was alpha star alpha plus beta star beta. The difference between here and here is that this X takes discrete values here, and there it takes continuous values. Yeah. And again, this is a number times its complex conjugate. So it means that this sum must be 1. In the example of the qubit, it's a special case. This, if you have our usual state of alpha 0 plus beta 1, this just means that the absolute value of alpha plus the absolute value of beta squared must be 1. Yep. Okay, this is just a rule, and again, does not change the physics. It's just so that our probabilities at the end kind of sum up to 1, and we'll see in a second. But before this, let's talk about having different bases for space, because this is kind of what makes quantum physics fundamentally different from classical physics. All right, so far, like in, classically you can also have random variables of different dimensions, even continuous random variables. We can do things on them, we can measure them and compute probabilities and so on. What we don't have is the possibility of changing bases. In the classical case, and I'll show you now in the quantum case, again, we have a vector base, so there's many possible bases. So let's call different bases, and we start with an example. We start with the qubit, because the continuous case is more complicated and we'll need more time for this. In the continuous case, it will talk about the position basis and the momentum basis and so on. And the qubit case is very simple. So we talked about the Z basis. That was 0 plus 1. And this was these vectors. Now, we'll talk about the X basis. So again, we need 2 vectors that are orthonormal and that span the whole space. Okay? So then let's take, instead of this 2, let's take this 2. This is 1, 1. And another one is 1 minus 1. We will see in a moment that they are indeed orthogonal. If they are orthogonal and there's 2 of them, that they can span the whole space, so that's okay. What they are not is normalized. If you put this plus this, that's 2. So we need to normalize them. And that's a 1 over square root. That's where kind of all the square roots come from in quantum mechanics. It's always this normalization condition that has squares. And how do we express this in this notation? Well, 1, 1, this is 0 plus 1. So that's state 0 plus 1 divided by square root of 2. And the other one is 1 minus 1. That's 0 minus 1 over square root of 2. They're kind of important states, so they have their own names. This one we call state plus. And this one we call state minus. And we use them a lot. Okay. So first we need to check that this is indeed an orthonormal basis. So you can start already try to test those conditions. And I'll do it on the blackboard. It's very slow and nice. So we'll see if this holds, if they are indeed orthonormal. And it's good because it's good practice for the thing we do again and again and again, which is just multiplying cats and bras. Okay, so far. So then we have to see if the product is 1. And this is the advantage of, so we could just take those two, take the basis element as vectors and do the inner product directly. But maybe it's good to get some practice with this Dirac notation. And so we put it here. So this was this state. This is the bra. And this, sorry. 1, 1. Okay. Oh, what am I doing? I mean, this is definitely true, but I didn't want to do this. I wanted to do the Dirac notation. I wanted to do 0 plus 1. And now 1 square root of 2. 0 plus 1. Yes. This term is this. This term is the last one. And now we know it's a beautiful thing about quantum mechanics that everything is linear. So you get these 4 terms. 0, 0 plus 0, 1. Plus 1, 0. Plus 1, 1, right? And now, because we know that the 0, 1 basis, the Z basis is orthonormal, we know that this term is 1, that's 0, and that's 1, right? So this is 1, 0, 0, 1. So then overall we get 2. 2 times 1/2 is 1. Success. You can do the same for minus minus at home, and I'll just do the plus minus. So this should give us 0. And again, 2, so if 0 plus 1, 1 square root of 2 of 0 minus 1. And now it's the same thing, except the 2 1s are going to cancel each other. So we get 1 over 2, 0, 0, 0, 1, 1, 0, minus 1, 1, and there's another minus here hidden, which is this one. That's a minus, right? And now again, this is 1, this is 0, this is 1, 0, and this is 1, but it has a minus sign, so the 2 1s cancel each other, so this thing is here, right? Minus plus is just a complex conjugate of 0, so that's 0, right? And the minus minus I did not do, but you can do at home, and or just believe me that it is indeed also normalized. So this is a valid basis. But now we want to know, well, how would I express some vector in this basis? Because this will be useful for many things like computing probability measures. And in the, mostly we'll use this in the complex, in the continuous case, but that's more complicated. So I'll just give you this one for now. So we want to express some vector in this. So we have psi equals some alpha 0 plus beta 1. And instead, we want to express it in some basis, in our basis plus minus, with some unknown coefficients, right? So let's call this, we can call it alpha x and alpha, and beta x. Okay. There'll be different numbers, of course. So how do we find them? So the first thing to see is that alpha x, that we don't know yet, equals, alpha x, which is a number we don't know yet. We can obtain it by just doing a stack, because it's really just recovering the wave function for this basis element, just like we did in the continuous case. And to show that this is true, you don't have to believe me. We can just see that it's true. So this is plus. And now we just take this state expressed in this form. So this is going to be alpha x plus beta x minus. And again, everything is linear. Plus beta x plus minus, and this is 0, and this is 1, so we get just alpha x, right? So it works, but of course this is not super, I mean, we don't know these numbers yet, so we cannot recover it from here, but we can just use this using the expansion that we already know. So this means we say, well, alpha x is plus times this. And what is this? This is plus times our state as we know it, because these coefficients alpha and beta we know. Okay. So that's alpha plus 0 plus beta plus 1. Okay, so now we just need to compute this inner products here. And they happen to be all, we'll show it in a moment, but this is 1 over square root of 2. And this is 1 over square root of 2. So let me just give you the result and then we show it. So you get alpha plus beta over square root of 2. And if you did the beta x, this would be minus inner product with this, and that would be alpha minus beta square root of 2. So what is only missing here that I did not show were these inner products, right? So let's show them. Or you can try to do it now. So what's missing to do is this kind of things. And again, this is nice just to practice the linear algebra, and yeah, they are useful in general. So what is plus? This is 1 over square root of 2, 0, plus 1 over square root of 2, 1, in a product with 0. And again, there we go. 1 over square root of 2, 0, plus 1 over square root of 2, 1, 0. And now this is 0 and this is 1, so you get just 1 over square root of 2, right? If you put here the plus and minus zeros and ones, they're all 1 except this one, because then I'll do it. Square root of 2, 0, minus 1 over square root of 2, 1. Times 1. So now when they multiply, the surviving term is the one that has a minus sign, so that's minus 1 over square root of 2. Okay. Okay, so we can always practice this, and in the exercise class on Thursday, you'll have more of this to practice. Good. Why are these bases called X bases and Z bases? That's because physicists worked out a representation of a qubit as a ball, as a point on a ball. And this can be useful to visualize some things like dynamics will become rotations of this ball and measurements are projections and so on. We'll talk about it later, but just to give you an idea, the thing you'll do in the exercise class is that, well, we take a state that's alpha 0 plus beta 1. We have here 2 complex numbers, right? Numbers. That's each complex number has 2 real numbers there, so it's 4 real parameters. And then I tell you, well, minus 1 because we have this normalization condition. So one of these parameters is fixed, it's just the norm of the vector. So this is from normalization. Then we take another one because this will be a global phase, which we'll see in a moment, that it doesn't matter for the outcome of local measurements. So this will be the global phase. And then I tell you for now that these 2 we don't have to care about. So then we're left with only 2 parameters, 2 real numbers. And it's like, okay, if you have 2 real numbers, then let's encode them as 2 angles. So theta and phi. And now this means now we can encode any qubit via these two real numbers. And you can think of them. We can find a mapping from these coefficients alpha and beta to points on a sphere where, like, if this here is my state psi, then there'll be this angle here and kind of this angle that makes with the x. You'll do all this in the tutorial. And the point of this is that then here are the states 0 and 1 will be in the z axis, hence calling the z basis, and the states plus and minus will be somewhere here if this is the x. And there's another basis that is a bit, people don't use it as much, just out of convention, is the y basis, which is plus I and minus I. You'll see all this in the tutorial. Okay? This is just to say that in the special case of qubits, we talk a lot about seeing them in a Bloch sphere, and this allows us to think, oh, unitary evolution is just rotating this to there. A measurement is just seeing the overlap with some axis. We'll see all this later. This is not so important. This is just so you know when it shows up. Okay. We need only one last element before we can talk about measurements, and that's matrices. So we saw a bracket, and now we need to find a ket bra. How do we express a matrix? Well, I mean, you have a big matrix, right? And you can express it as a sum of every element here, and every element, you can think of it as a sum of this, the other way around, sorry, of the product of a column and a row. Right. This would be a number if you did it this way, but if you do it this way, a column versus a times a row, this gives you a matrix, right? And this would be a matrix maybe with this basis element, and then you have another one, and so on. What I mean is that you can express any matrix as some sum over all the basis elements. This is in the discrete case of the ket times the bra. So now this is a matrix element and times some coefficient, which is a number that will show up here. It's just called, this is an arbitrary name, has nothing to do with the alpha and beta before, it's just a coefficient corresponding to column X and row X prime. Okay. This will be very useful for measurements in a moment. Okay. So now we can talk about measurements, and it's going to be a bit like the offside rule. If someone just told you that rule out of nowhere, it'd be like, why would it be like this? But then once you look at the game, you see, oh, you actually need some rule like this, otherwise the game would be very different, and there will be not kind of the same, just not the same sport. In the case of the rule for obtaining, computing like probabilities of quantum measurements, first people discovered as it is, and more recently people doing research in quantum foundations try to see, oh, what would happen if we didn't have this rule, but if we had like a slightly different rule, and try to vary it in many ways. And so far, what all the research shows is that, yeah, you just get a very different physical theory if you change this rule even a little bit. Then, for example, you cannot have dynamics, or you just don't get systems that are stable enough to form molecules, and so on. Okay, but for now, I'll give you as God-given rule. So suppose we want to measure, for example, we have a particle and we have a continuous degree of freedom, and we say, well, this represents a position. Okay, and now I want to measure the position of the particle. And let's talk first about the very, very ideal case. So and this is the ideal case. You never do this in a lab. And this is, let's call about measurement with respect to a basis. With respect to some basis, and I'll just use here a different letter that we haven't used yet. Why? Well, then the rule is this, that the probability of obtaining outcome Y. So I measure the position of the particle. I call the position Y for now. And I ask, what's the probability that I find the particle precisely in point Y? Okay. Then the probability of obtaining outcome Y, say, or corresponding to Y, for some quantum state psi, this is given by psi y psi. I write it like this because it will be easy to generalize it later, but this is just, sorry, let me write it even like this, so you can see. Look, this is the vector that the state that you want to measure. And this is it's a matrix that corresponds just to outcome y. Okay, so it's the cat and the bra. But a simpler way to look at this is to just see, well, it's this inner product modulo square, right? Because you have this inner product times this inner product, that's the complex conjugate. Okay? This is why we spend so much time talking about the inner product. Okay, so this is the God-given rule, and it's called the Born rule. Okay? We take it for now, and we'll see an example. So, examples. All right, so suppose I want to measure the position of a particle. So far this y could be anything, any Hilbert space, but now let's say it's a continuous case. So this basis that we talk about so many times. Yeah. With the x being a real number, then the probability that I find my particle at position x, well, this is given by this in the product. But we already computed this, right? So we saw that this, if you go back in your notes or on YouTube a few minutes, what we saw before, just before the break, was that this in the product was the wave function at position x, right? And now we just do the modulo square. So this is why the modulo of the wave function is such an important thing in quantum mechanics, is because it gives us, it really gives us like the probability of getting a certain outcome. And this is also why it's normalized, because if I want to measure the position of a particle and I ask what's the probability that I find it here, plus the probability I find it there, plus there, all over the real line, it better sum up to 1 because this particle must be found somewhere, right? So that's why if you have the sum of the integral of this thing, sorry, if you have the integral of this thing over the real line, it should be 1. Here's another example. We'll see a lot of this soon, but first I'll do it more physical. But before that, we see another example in the qubit. So we have again our favorite state. I should just bring a sticker with the state. And now suppose we want to measure it in the x basis. Yeah. And this can, like physically, it can mean things like, suppose our qubit is a photon and it's polarized light, and they ask, you know, if you go to the cinema and you get these 3D glasses, what they do is that they just let in light that's polarized again in a certain direction. So you can ask, what's the probability that this photon will pass through, for example. If I rotate my glasses to be aligned with this basis. We'll see this in an example later on in the course. But okay, but if you do this, okay, then what's the probability of getting outcome plus and you know, you can put the cat here or not. When I measure psi, well, this is plus tac square, and that's the inner product that we spend a long time computing. That was what? Alpha plus beta square, and then here we had the square root of 2, but square root. what's the probability of getting minus in the same state? Minus tag, and that's going to be alpha minus beta square root of 2. So to be even more specific, so suppose that now my state is just the 0 state, so in the z basis, and I ask, oh, if I measure it in the different bases, in the x basis, what's the probability of getting plus? Well, that's just this square, and this we saw that was 1/2, and the probability of getting minus 0 square, which is 1/2, and of course the two probabilities sum up to 1. I think you see maybe already in this tutorial, is it true? Yes, that these probabilities in the case of qubits, we saw this Bloch sphere before. It's here, it's up there, it's too far away. That this correspond kind of correspond to the angle that the state makes, correspond to the kind of the inner product between this vector and this vector, and depend on this angle between the bases in which you're measuring, which is an axis, and your vector state, your state vector. Okay. And now, so this is the rule. Yes? Yeah, here he is. Yes, you're right. Yes, very good. Now, remember that I told you just before that you can't forget that, like, normalization is fixed and that the global phase does not matter. And that's what we'll show now. And again, it's a very simple computation. Okay. Where was I? There we go. So normalization just means, as we saw before, and I told you a few times now, this just means that the sum over all basis elements, the probability of getting x, when measuring state psi, this should be 1. And that's just sum over x of this, right? In the continuous case, this means the square of the wave function modulus. The other thing is the global phase. What do I mean by this? So take a system, any system, it can be continuous or discrete, doesn't matter. And now we had our state psi, can be any state in any system. And now let's construct a new state by saying, well, I just give it a real phase. So this is just, yeah, this has modulo 1. It just gives a complex phase to it. Let's call this state psi. And now let's say, well, how do the probabilities change now? But so the probability of getting some outcome x with psi, well, That's again the beauty of the absolute value is that when I expand this, so this is just I some complex number. And now this complex number can come outside. Times this is just one, right? Because it's just one, right? This is that times e2 minus I phi, which is e to the 0 overall. So that whole thing is just one. So then you're back with this, but this is the probability of getting x if your initial state was psi. That's why in general, you'll see that we can, when you do, for example, the Bloch sphere, we can get rid of this parameter that gives you the global phase. However, it doesn't mean that the global phase is useless because no quantum system exists like in isolation. So as soon as you have this quantum system now interacting with something else, or we want to do a global measurement, then this phase can become important. It just doesn't matter if you're only thinking about operations and measurements acting only in this little system. Good. So this was all I wanted to say for today. So let me just tell you a bit about the course logistics. First of all, if you want to come in person, I'm happy to have you here. If you want to watch online, that's good too. The only thing I advise is maybe, I mean, from my experience last year, the students who did better were those that kind of self-organized in groups and they would discuss the lecture together or watch it together or so on. So make friends and watch the thing together. We can answer questions both in person and online. We have office hours, which for now are on Zoom. If there's a lot of demand, then we can arrange to meet somewhere. And that's in the afternoon of Tuesdays. What else? The tutorials are on Thursday, and they're also, everything is streamed. The assistants are Lidia and Nurgalieva, who we already met. And they will more or less take turns every week because we only have one room. There's anyway not so many people in the room. We'll see, like, we'll adapt. If at some point we need to go fully online, we'll do that. There are lecture notes. They are from last year, and these were students who typed the lecture notes. So if you see any typos or so, let me know, and I'll try to update them as we go along. Yeah, the exam is a written exam. We wrote some examples from last year. We put them on Moodle. Don't be scared. If they look too complicated, just think that by the end of the semester, you'll be able to solve that kind of problem, which is cool. And also one more thing, in the tutorials, sometimes we give exercises that are a bit more difficult just to show you, in principle, if you had all the time in the world, you already have the tools to solve this kind of problem. It doesn't mean you should be able to solve it now. It's a way to test your knowledge. Okay? It's more for inspiration. Yeah, and that's it. So in the next course, in the next Thursday, we will talk about more physical measurements because this is way too ideal. You can't implement this in a lab. And then we'll talk about dynamics, and then we'll start having fun. So yeah, very good. Thank you, and see you on Thursday. Can you end the meeting?